So our next unit is called the periodic law, and it's going to be a unit that's going to talk a little bit more extensively about the periodic table, including the groups, some of the properties of the groups, and then the big part is going to be the trends of the periodic table. So it's a fairly quick unit, and the good news is there is no math in this unit. So let's get started with talking about the very first periodic table. By about 1850, scientists knew of about 70 elements that were known, but there was no way they had of arranging them. So the first guy to do this was a Russian scientist by the name of Mendeleev. Both ways are usually accepted for pronunciations. He was the first person to take these elements and arrange them, and what he did is he listed on a bunch of cards, lined them up by their masses, and when he did this, he noticed that there were some patterns that appeared at regular intervals. And so, like I said, he was the first one. He published his first table in 1896, and I believe that's a typo in your notes, so make sure you change that. It was 1896. And what he did, which was kind of cool, is he left blanks in his periodic table for undiscovered elements, and he predicted the properties that they would have. And in many cases, he was actually right. But the problem with the way his table was arranged was the fact that when he arranged them by masses, there were some gaps that didn't line up correctly. So for many years, this was the table that a lot of scientists used until a better one came along. So in 1911, after the discovery of the nucleus, Moseley, his name was Henry Moseley actually, discovered a new pattern based on the atomic number, which if you recall is the number of protons in the atom. And he noticed that when they were arranged by atomic number instead of atomic masses, the gaps or the things that didn't work in the original periodic table actually made it work better by going by the atomic number. So the new periodic table, which is the one that we still use today, is arranged by atomic number instead of atomic masses. And that is a good test question. A lot of times we'll ask, what was the original periodic table based on? And that would be masses, atomic masses. And then the current or modern periodic table is based on atomic number. So that's a good thing to know for a test. So that brings us to the title of this unit, which is called the periodic law. And remember, anytime you see the word law in class, you know it's going to be on the test. So what the periodic law is it states that the chemical and physical properties of the elements are periodic functions of their atomic numbers. And what we mean by periodic functions is that they show up periodically. The same properties or characteristics are showing up periodically. That is actually why the periodic table is called the periodic table. The arrangement of the periodic table is arranged, as we saw last chapter, based on their electron configuration, but it also works out that the atomic numbers are arranged so that the elements with similar properties are falling into the same group or family. And we'll see in a minute which ones are the groups. So groups are your vertical columns that are numbered 1 through 18, and they're the ones that go up and down. And in your groups, remember, you have similar properties. So sodium has similar properties to potassium as you go down the group. The periods are the horizontal rows that's as you go across the period, and they are numbered 1 through 7. And periodicity, which is a good definition to know for the test, is the similarities of the elements in the same group can be explained by their electron configuration around the nucleus. And I noticed that I got of the elements in here twice, so let's cross that out. And so we have to make sure we know which ones are groups, which ones are families. So make sure you know those definitions as well. So group 1 is known as the alkali metals. And some of the characteristics of those are that they are soft, silvery metals, so soft in fact that you can cut them with a knife. They are the most reactive of the metals. As a matter of fact, they get more reactive as you go down the group. So francium would be the most reactive. of the ones in group 1. They are never found free in nature because they are so incredibly reactive that they're always bound in a compound. They react violently with air and water. And of course, if they're in group 1, they all have that NS1 configuration, meaning they end in 1s1, 2s1, etc. Okay? And because they do this, and they have that one electron, they tend to form a +1 ion. Group 2 is called the alkaline earth metals. They are still very reactive, but they are less reactive than the alkali metals. They too are never found free in nature. They're almost always bound up in the compound. They are harder, denser, and stronger than alkali metals, meaning you can't cut them with a knife. And then they end, of course, in that NS2 configuration. So we would have 2s2, 3s2, etc. Because they have those 2 valence electrons to give away, they tend to form a +2 ion, a positive charged 2 ion when they're participating in compounds. Next up, we have our transition metals. They are all metals which have the classic metallic properties that we're used to thinking of, like malleability, which is hammering into thin sheets. Think of foil. Ductile, which is pulling it into a wire, copper wire, and a lot of electronics as an example. Metals have luster, which means they are shiny, and of course metals are good conductors. The transition metals are less reactive than groups 1 and 2, and they're also harder and denser than the alkali earth metals. And if you remember from last unit, the electrons are filling the d sublevel. Next, we have groups 13 through 18, which we know as the P block. And there's really only 2 groups in there that we give actual names to the groups, and one of those is the halogen groups. It has 7 valence electrons in the outer s and p orbital, because remember they're all going to end in s2p5, which is where we get those. They like to react with group 1. They are the most reactive of the nonmetals, and because they only need 1 more electron to get to 8, they will tend to form a -1 ion when they're forming compounds. Within the P block, we have metals, nonmetals, and metalloids. Remember, the metalloids have properties of both metals and nonmetals, and they tend to be very good semiconductors because they'll conduct electric current somewhat, but not so much that it fries a circuit board. And I believe this was a mistake in your notes, so make sure you make note that that is the P. They are in the P block, and I think your notes say D block. So that brings us to group 18, which are the noble gases. And the noble gases, as you know, have 8 electrons in the outer S and P, because it ends up being S2, P6 for a total of 8. And remember, we call that an octet. All of them within this group are gases. They tend to be very unreactive due to their high stability of having that octet, because 8 is great. So there's very few compounds that actually participate in noble gas bonds, but there are a few. Now, together, when we put this S and P block group together, we call this the main group, or the representative elements. And the reason they're called this is they're the elements that participate in the majority of the reactions. All right, here we have the inner transition metals, which are located in the F block, which is the 2 lines at the very bottom. And the 2 parts of the inner transition metals are the lanthanide, which is 58 through 71, and they are shiny and reactive. And of course, they're filling the 4F orbital. And then the last one on there is called the actinide series, which is 90 through 103, and they are very unstable. They are radioactive, and of course, they are filling the 5F orbital. Remember from nuclear chemistry, anything above 92, which is uranium, is not naturally occurring. It's usually man-made or syndicated. So that brings me to hydrogen and helium, which we call the oddballs, and that is because they're up there all by themselves. Even though hydrogen is in group 1, we absolutely know that it is not an alkali metal. The only reason that it's put there is because of the 1s1 electron configuration, so it matches in there. And of course, helium is a noble gas. It is also in group 18, but we also know that it is not have 8 electrons in its energy level. It only has 2, but we put it over there with the noble gases because it behaves as a noble gas in that it's very stable and does not participate in reactions. So that brings us to the end of this video lesson. You can stop the lesson here, or you can keep playing for my jokes. So since this lesson was about the periodic table, I thought I would do jokes where the punchline is an element. So here we go. What do you call a clown in jail? Well, of course, he is a silicon. What do you do in a play? You act in them. And then who is Mr. Moni's enemy? He's anti-Moni. All right, you guys have a good day. That's all I've got. All the good jokes are gone.